Hello everyone, I wanted to continue our discussion about Tuxedo. So a brief recap of what Tuxedo is. So if you have a particular block with some transactions, what we say is that these transactions don't have to be immediately executed. So we don't have to update the state based on the transactions in this block. We update the state corresponding to these transactions in a future block. Okay, so this is bi plus z. Okay. And this block of course has its own transactions. Okay. So these are executed and the state is updated in a later block. So this is a delayed execution of transactions. So that's the main idea of Tuxedo. So these transactions are put into a queue which the CPU keeps executing one after the other. So maybe Ti goes somewhere here and there's Ti minus 1 and so on. Okay. So this gave us some advantages in that we sort of bypassed the verifier's dilemma problem. So the verifier's dilemma problem came in that because we had to execute the transactions immediately. So of course, what state does this particular block have? Well, it has the state corresponding to the transactions which were present in a block, Z blocks in the past. Right? So those transactions have to be executed by this point in time. So we've separated out transaction ordering and transaction execution. We are not doing both of them simultaneously as it is done in Ethereum. Okay, so this was the main idea of Tuxedo. So what can the maximum gas be for a block, right? So let's think about it. Effectively, on average, we are getting one block every, let's say, interval time of blocks. So for example, in Ethereum, we have one block every 15 seconds. And in Bitcoin, it's a little bit more than that. It is, right, every 10 minutes you get one block. Okay. So, in any queuing system, the input to the queue should be less than the output speed on average, right? Otherwise, the queue would keep building up to infinite length, which is not what we want, right? We want a set of transactions to be executed by a particular deadline in the future, which we've set to be some Z blocks, right? So we want the input of the queue to be in terms of computation. Remember that we are executing these transactions one after the other. The input rate into this queue has to be less than the output rate, right? So essentially, one block's gas limit should at least be less than or equal to the computation possible in 15 seconds. So with Tuxedo, on average, one block's gas limit should be less than or equal to computation possible in one interval time. And in theory, you can push the limits and you can make it close to this computation possible in one interarrival time. So right now Ethereum is using only 1%. So the Ethereum gas limit is roughly equal to what computation can be done on a high-end desktop, let's say 1% of computation in 15 seconds. Okay. So in theory, we are pushing things up almost 100 times in the limit. I mean, sort of in the best case. Right? But of course, in practice, we'd have to look at what exactly we can do in practice, and some of the analysis in the paper looks at that issue. Right? So the thing is, even if let's say we set this deadline to be 5 blocks in the future, this 5th block doesn't exactly come 5 interarrival times in the future. It might be only, instead of coming in at 5 times 15, it might come, this 5th block might show up much earlier, because this block generation process is a random process, right? So we have to take that and do some queuing analysis to figure out what's a reasonable amount of computation that we should allow in a particular block. Okay, but before we look at those issues, let's look at another more fundamental issue. So one of the reasons we said that Ethereum does the computation right away, it doesn't put anything in a queue to do delayed execution, it does it immediately. And the reason is that you want to know that the contents in these transactions are meaningful. You don't want somebody to put some junk in there, or, an invalid transaction or anything like that, right? And also we said that you want to make sure that all the people who put in transactions are actually paying for the gas, right? And now since we are delaying things, then what's going to happen? Okay, so that's something we have to think about. So let's just recall why Ethereum does computation immediately. So one is that to eliminate transactions that are invalid, and they may be invalid due to, let's say, wrong syntax and so on, right? Or even if the syntax is correct, maybe the person who sent the transaction is not authorized to run some functions. Right? He might try to spend some money which doesn't belong to him, for example, right? Or whatever, right? Might try to call a function he's not allowed to call, right? So this sort of thing won't happen with Ethereum, because people run the transactions immediately when they're creating the block itself. So a second reason is that transactions must pay for their gas, right? So they will say that this is the gas for my transaction, and I'm paying the maximum amount, right? I'm depositing it at the beginning of the transaction, and if at all I run out of gas, then there are some rules to be followed. The person will lose all his deposit, but and the state will be pushed back to as if the transaction did not execute, right? And of course, if there is if everything executes properly, then he gets a refund. So this is very critical, so that people actually pay for their gas. Otherwise, it's going to be an unfair system, right? These are various reasons, and of course, the third reason we said is that state must be put in. For light clients, right? That's what we had mentioned in an earlier class. So in case a light client only has the block headers, through a Merkle proof, so anybody can prove what the state is, right? So there are various reasons like this, but let's focus on these two for now. So we've done something clever. We've delayed the transactions, we've delayed the execution, but then how do we deal with these issues? I mean, what if there is some invalid syntax or something like that? Because after all, we said that when you get a particular, when you create a block, you can just take transactions in the transaction pool, right? And what if there is something wrong with it, right? And so then there is an attack possible. Somebody might just put junk. He might say that this entire gas limit possible with Tuxedo, I am putting in my transaction, and then the transaction doesn't do anything. You just throw it away, right? And in that case, what happens, right? And what if he hasn't paid for his gas, right? So what are we going to do? So clearly, just taking a set of transactions in the transaction pool and dumping them and creating a block and sending it out is not going to work, right? We have to do something a little bit different from what we had said earlier, right? And at the same time, we don't want to do the computation right away, because then we are back to Ethereum. We will face the verifier's dilemma and we are back to Ethereum. Okay. So what should we do? Let's think about it. What sort of we are, let's say we are willing to do a little bit of computation for a particular transaction, but we don't want to execute the full transaction. Okay. So what can we do? So let's think about it. So do a little computation per CIT, but not the full computation. So one thing we could do is we could do a syntax check. Okay, so that's fair enough. I mean, we could do some basic things like that. Okay. Another thing that we can do is to handle the second issue is that we can collect gas right away. I should say we do this computation immediately. Okay. So what we are going to do is that in BI, let's say that there are transaction set is TI. We are going to collect gas immediately and of course we are going to delay the CIT execution and we have to finish the computation before this deadline. Right, so this state corresponding to this has to be updated over here. Right, so we have a little bit of time, and we want to exploit that. Okay, but so we collect the gas here. Okay, and then what do we do, right? So let's say somebody says that I want let's say equivalent of even 1 second worth of Ethereum computation, right? So that's a lot of computation, way more than the 100 millisecond or whatever which the current block has in Ethereum for computation. Right? So we could say that, and then there's some charge. If you want 1 second, then you have to deposit certain amount, and the computation could, in the worst case, be done up to here, right? It could be delayed here. Let's say this is the deadline. So when are we going to refund this amount? Okay, and intuitively you can think that we are going to refund the remaining gas over here. So we refund the leftover gas in BI plus A. Okay. So effectively, while executing these transactions, when we update this state, we will have to reimburse whatever remaining gas is over there. So how do we understand this? So let's say that there is a particular transaction, let's say T0. Normally we execute the full transaction, but let's say that this has two parts. Let's say that there is a gas part, and let's say that there is another part corresponding to the computation, right? So this is where the logic of this particular transaction is. So what we are going to do is that when this transaction shows up in a block, this is executed immediately. This part of the code of the transaction, and this is delayed. And this is done for each and every transaction in a particular block. Right, so what we do is we can do a preliminary check to make sure that all the transactions have valid syntax, some very simple quick check, right? And then what we are going to do is we are going to collect all the money for the gas, right? So there will be some gas specified over here for a transaction, right? So how is this going to fix any of the problems? Well, if we go back to this, we said that transaction must pay for their gas. So somebody can't launch an attack and just say that I'm going to use a lot of gas and not pay anything. It's not that we will find out later. He will have to pay up the gas amount right away. And if at all, of course, the transaction doesn't do any computation, let's say, we will have to refund some amount. Okay, so So it's just that he cannot end up just putting his single transaction in a block and say that it uses up the whole gas limit, but not do anything. Right? So just let's think about that attack again. So the attack would have been that say T0 uses up full gas limit of a block. Okay, but so what there are different variants of this attack, but let's say that don't pay for the gas, right? Or there could be other things that we can do. Pay for the gas, but don't use much gas. Okay, and either way, this is sort of like a denial of service attack, because no computation is done, no useful computation is done by the system. Okay. So what have we dealt with till now? Well, we have fixed this problem because I mean it could be that there was some genuine heavy computation in the block, but somebody didn't pay the gas upfront. Okay, that might have happened, but we fixed that problem by saying that we collect the gas right away. If a transaction doesn't provide the gas appropriate for its claimed gas limit, then the transaction is not included in the block. Okay. Okay, so this is taken care of. So we will only have transactions in a block which have paid upfront for their gas. So what the person does after that, I mean what this computation does after that is not such a problem, because even if it if there is something wrong with the computation, or if it does take up a lot of computational time, that would have been paid for by this gas. Okay, so the second issue is a little bit tricky, because what if somebody says that I'm going to use up the full, let's say 15 seconds of computation time, whatever is allowed by the block, I'm going to use it all up, and he actually pays for the gas, but then this computation is done very quickly. Then again we are ending up with a system where just no computation is done by the system, because somebody said he's going to do a lot of computation, but he didn't. And normally in Ethereum we would reimburse him the gas, right? We would refund him, so he would get back most of this gas which he had paid for initially. Okay. So that has to be dealt with, and of course in the paper that we have published in Sigmetrics, these fine-grained attacks haven't been considered. But what we have proposed in earlier versions, the initial drafts of the paper, is that there is a minimum refund, or there is I should say a maximum refund. So we are going to refund, let's say either the minimum of unused gas, or let's say a certain fraction, let's say half of gas limit of the transaction. Okay, something like this, right? So suppose the unused gas is very high, you're only going to reimburse him half of what he initially deposited, right? Of course, if the unused gas is very low, then he's going to get this unused gas. It's going to be reimbursed. So this is the amount that he's going to get back, right? And this is going to take care of this other attack. It could be an attack, but it could be just even an honest person just says that I need a lot of computation, but he doesn't do much, right? But effectively, you want people to make use of the computational time that they claim they want to use, right? So you can only maybe we can reimburse half or some other fraction which we think appropriate, right, to reimburse the person. Okay, so this is at a high level what we're doing, but as we see, the other tricky things can happen, because normally the entire computation is done in one shot in Ethereum for a particular transaction. Now we are splitting it up. So part of the transaction which is related to this gas, we are doing immediately, and the rest of it we are delaying a little bit into the future. Okay. So a question comes, what about the ordering of transactions? We want everybody's computation to be the same, right? And although the transactions may be ordered in a particular way in the blockchain, part of the computation is done at one point in time and part of it is done later. Okay, so the question is everybody going to do the computation in the same way? Because this delayed computation could be done at different points in time for different people. Of course, the state has to be updated at a particular time. Let's say in block B, I plus Z for the computation of this particular block. But this, in case the queue was empty, the CPU queue was empty, this might have been done immediately for somebody. But somebody who had a slower CPU might actually do the computation a little bit later. Okay. So the question comes, is everybody going to do the computation in the same order? Right? So let's look at one issue that might come up. So let me just write that down as a problem with delayed computation. With immediate gas collection. So let's write down some things formally. So this gas collection is immediate. And let's just call this as tier 1 in the blockchain. Okay? And so we could have transactions which do all their computation immediately, So suppose it is a transaction which doesn't have any tier 2 computation. We could actually have a full, computation also be done here, but we'll ignore that for the time being to make it simpler. Okay? So let's just say that all the computations are, let's say, these CIT computations, and the computation happens in tier 2. So let's introduce some additional notation, and so the state is denoted by, let's say, Pi, okay, and here the state is denoted by Si, okay, and we will refer to the let's say the transaction parts which are executed. So we have to introduce some new notation over here, and so here we'll call this phi I, and this as usual we call Ti. Okay, so this is this corresponds to all the gas collection of all the transactions in Bi, right? And this is all the heavy computation done for all the transactions in block Bi. Okay, so what is stored in Bi? So Bi of course has phi I and Ti. Okay. So we're going to store Pi, which is because I mean this has to be immediately executed, and so we can update Pi. Okay. So what is this Pi, you might think? Well, I mean, you're paying some gas, so there has to be some transfer of one account to the other, right? So the state variable corresponding to those. So all the state variables paying the gas, right? And the other variables which are updated with the computation are stored here, right? So here we said we want to store the state corresponding to the past execution, right? So this is stored in Bi, right? And let's call the refunds okay. So the refunds Ri correspond to Ti. Okay, so this there is some code corresponding to this, okay, and it could be built into the smart contract, or maybe there is some standard code which is applicable to all smart contracts for reimbursing, right? So whatever unused gas is there, we have to reimburse, of course, using some formula like this, right? Just so that in case not much computation is done, then you actually pay a lot more than the gas you used. Okay. So how are all of these things related to each other? So Pi is updated when you execute some code, right? So this is just saying I'm going to execute some code, and of course you have to take the previous state and you have to take the reimbursements. So remember what is going to be reimbursed here, where you had an old block Bi minus Z. So these transactions had to be executed and the reimbursements had to be made. Okay. So this code corresponding to the reimbursements of the old transactions are taken, and of course the gas payment for the current block, okay, these parts of the transactions are also taken, and so all of those are going to update this state, right? Okay. And what about let's say S I minus Z? Let's say this happens, of course you'd have to take the old state into account, and you have to execute these transactions, okay, in the old block, right? So this is going to update this state, and it's also going to tell us what is the reimbursements. Okay, so it's going to update this and it will tell you how much is left over when you execute this. Okay, and this you have to plug in over here and you will get PI, right? So this is roughly what Tuxedo does. So what can go wrong? We said that there is some tricky issues happen because part of the computation is done right away. Like we said that this is done right away, the phi I, but part of the computation is done later on, right? Okay, so when we update the block in the future, Z blocks in the future, that's when we would execute TI. So what is the problem? So I want to ask a question. So can PI and SI have overlapping state variables? So this is an issue because SI gets updated later and PI is updated right away. Okay. So just let's write down what is happening over here. So we have BI, and what is executed. So we are executing Ri minus Z and phi I, and we are executing Ti minus Z. Okay, so this is what must be executed. So must be executed by BI, right, by this deadline, but this could be executed earlier. Okay. So of course here everything increases by 1. And when we go into the future, BI plus Z, so there is of course these have to be executed immediately. So I'll just say this. So this is immediately executed, and for this there is a deadline, but it could be executed earlier. Okay. So now suppose what was there in this block, let's think about it. So there we said that it has phi I and Ti. So this transaction has already, suppose there is a particular transaction which belongs to Ti, right? There is some T0 in there, and maybe it has something to do with an auction or whatever, right? Or there's a particular payment to be made. So there's some complicated logic, and Ti has some input variables, let's say. Now what could happen is, see, Ti is going to be executed, could be executed all the way here, right, just before BI plus Z. It could be executed earlier, of course that's a different problem, but Suppose Ti is executed just before Bi plus Z. Okay, so just before Bi plus Z. So what could affect the state variable A? And the outcome could be very crucial. Who wins the auction, let's say, might depend on A, right? Or who's trying to buy something, right? Whatever happened. Let's say there's a game in a particular transaction. So what happens in that game might depend on the state variable A. And notice that these are executed immediately. These are executed So what might happen is that somebody may modify variable A through any of these. So T0 we are saying gets executed here. Suppose, right? So what's going to happen is that somebody has modified A. He's already seen that the transaction has gotten to the block here, and he realizes for me to win the auction I need to modify a particular variable A, right? And so he might do something in one of these executions, these 5 parts of the transaction, so that he modifies A to suit himself. Okay, so this is an issue. I mean, somebody could it's not fair to others. Let's say that everybody has put in his bid, but maybe A is a bid of somebody else, right? And he might modify his bid in these future transactions, right? There could be some mischief done over here, right? So the state information for this transaction is being modified in the future. Okay. So if we lose the ordering of transactions which was there in Ethereum, and what was this ordering? So future transactions could not affect execution of past transactions. Okay, so that ordering is lost and it might cause some problems and newer types of attacks and so on. So what else could go wrong? Okay. So there are some concurrency issues. Okay, so we are saying that if you go back over here to this figure, these are executed immediately, these 5i's, right? But these ti's could be executed anywhere. Okay, so for example, ti is input into the block here. It could be executed here, or it could be executed here, or it could be executed here. Okay, so one miner, they're just putting these transactions in their queues. Somebody might have an empty queue because he has a fast CPU and he executes this immediately. Whereas somebody else, who has a slightly full queue might execute it later. But of course, this is the deadline, so they better execute it up to this time. Okay. So when they are going to execute TI, and so we have, let's say, one miner executes it this way. Okay, so this is in BI plus 1 and so on. So let's say miner 1 executes TI over here, and another miner two might execute it, let's say, over here. So the transactions are not executed in the same order by different miners. So we created more problems when we solved the earlier problem. So the earlier problem was gas is not being paid, somebody might launch an attack. So we said you pay the gas immediately and you do the computation later. But then we are running into problem that different miners might execute these later, and if all of these are updating the same state variables, how do you know that everybody is going to get the same state finally? So how do we deal with this? So our solution for these just mentioned problems is to have the state separate. So tier 1 and tier 2 so we can just say for Ethereum it might be accounts are separate. So an account which is used in phi cannot be used in ti and so on, right? So that's how we ensure that the state variables are non-overlapping, okay? And what we've suggested in the paper so really what we should have said is something like this, but what we have suggested is that you used actually different tokens in tier 1 and tier 2. So let's say token 1 and token 2 in the two tiers. Okay, so this might come in for some criticism because it's deviating from Ethereum, right? Because Ethereum you have just the Ethereum token, but of course Ethereum can have other ERC tokens within it, right? So what we suggested is you use one token for paying the gas and the reimbursements also, and another token for all the computation that is done here, in TI. Okay. So that's a little bit controversial, but the question is, do we really need it or not? And the answer is not really. So when we talk about sharding, we will see. So in sharded blockchains, you actually have multiple blockchains working together, each in a different shard. And you can have payments between the shards. Okay, so some care has to be taken care to ensure that there are no concurrency issues and so on. Right, when you pay from one shard to the other. Okay, and you can think of these two tiers as being in some abstract level. It is almost like something like two different shards, though it's not quite the same. Okay, but the point is that if you can make payments from one shard to the other, then why can't you use the same token, from here to in both the tiers, and you could use the same token in both of these, right? But you would have to be a little bit careful when you make a payment from one tier to the other. We'll be able to push tokens from one tier to the other, right? So that is possible to do, and of course we didn't deal with it in the paper because there was a lot, page limit, and there are lots of other issues which we had to study.